And we'll go ahead and get started on this. Like I said, it shouldn't take us too long, hopefully, to get through this material. I actually have two slide sections that I'm going to look at, but not necessarily do everything in the second one. So I'm going to primarily focus on this first one. Okay, so today we want to just talk about a little bit of an overview and introduction to the GPS concepts. Like I said, a lot of you guys are pretty familiar with this, so that shouldn't be a big deal. I'll talk a little bit about GPS signals and how they work. Again, that if you're dealing with GPS a lot, you probably already know a lot of this stuff. But if you haven't, this should be a good introduction. And then when you get into some of the other classes where they'll use it, you'll see this stuff again. Talk about the GPS coordinate system. A lot of people don't kind of understand when you're going out there and you're getting state plane coordinates, GPS doesn't work in state plane coordinates, or really what I should probably say is in GNSS, Global Navigation Satellite Systems. So we'll talk a little bit more about that. And positioning fundamentals, get into some of those issues and errors that are very important when you look at GPS observation. And then I have a second PowerPoint slide. We're not going to look at all of it, but we'll just do this. This was the major one we'll hit. Okay, so obviously most people understand GPS and some of the things, but for surveying, it provides a lot of things that definitely revolutionized surveying. But basically, of course, we get timing and position information worldwide, 24 hours, anytime. As long as you can get access to your satellites, you're going to have that. You got high reliability, low cost. In fact, really, it doesn't cost us anything to use the service other than our tax-paying dollars. But and of course, if you have to buy a receiver, that's your biggest cost. But other than that, low cost, high reliability, operational day or night. It's weather independent. Line of sight is not required. Now, we got to be careful in what we're saying there. Line of sight from the receiver to the satellite is required. But what we're talking about is if you want information between, let's say, two fixed monuments in the ground, you don't have to have a line of sight between those monuments. All you have to do is be able to observe at a receiver position in one monument and at another one. So there is line of sight that's required to the satellites, but not from monument to monument. So that's what that's really saying. Obviously, it's revolutionized many, many things, not just surveying operations, but when we look at surveying, of course, the ability to bring control anywhere very rapidly, it's just incredible. And of course, lots of people are doing layout with them, machine control, which is just quite an incredible thing where all of the information is derived into coordinates that are downloaded to your dozers and your other heavy equipment, and then that's all pretty much driven by the GPS satellites. And of course, this has gained worldwide acceptance. And not only that, but we have other systems available to us as well. So the global positioning system, which when you say that, primarily that is the United States system. Okay, that's not the world system. So they typically use GNSS now for global navigation satellite systems, and that's really the constellation of other satellites, which we'll talk about here in a little bit. But GPS itself actually grew out of our space program, and it was primarily driven by global navigation and guidance that was done by the military. So a lot of it was military driven. And in fact, the military still runs it essentially. A little bit on the historical development as we see. Satellite navigation actually started in '58. First positioning system was developed. It was called the NNSS. So that was an acronym for Navy Navigation Satellite System. And another term was transit, and it used what's called a Doppler shift principle. So a little bit different from what we're doing, but you're measuring what's called a Doppler shift, which allows you to determine measuring two different frequencies. And Doppler shift is, you guys are probably familiar with that, but when you hear, let's say if you've got a vehicle driving down your street with a really loud music, and if the windows are down, you can hear it. If that vehicle's driving at a very fast rate towards you, the velocity is increasing, and so what it does is actually increases the pitch of the sound. And as he drives past you, right past you, it's at its normal pitch, and as he drives away from you, it's lower in pitch. And that's the difference there, is that's that Doppler shift. So what you're measuring is that. This satellite constellation varied from 5 to 7 satellites, and it was primarily in polar orbit. So it was an altitudes of 1,100 kilometers, which is really low compared to the GIS ones are way up there compared to that. This was primarily developed to aid the Polaris submarine fleet. So those were our nuclear submarines that were up there. And it was authorized in '67 for civilian use. So prior to that, it was strictly military. There probably at that time weren't too many surveyors or civilian surveyors or anybody like that that was engaged in it either. You probably had to have some pretty pricey equipment. So enter the next phase was what was called the navigation, satellite timing, and ranging. And so its proper name is that, and then what we call it is Navstar, and this is your GPS. So this is what we now call, or most people just call, GPS. It was developed by the DoD, and it began development in 1978. The approximate cost in that time frame was $12 billion. Considered fully operational by 1993, so we launched our first satellites in that 70s period, and then by 93 you had all the full constellation of satellites that were there, and of course they continually update new satellites. So this one was basically a very different system. Instead of using a Doppler shift principle, it was based on observation of transmitted signals. So essentially all you're really getting at, and we'll talk about that, but basically it's just telling you a range from the satellite to where your receiver is. And really all you're getting is timing information, which gets converted into what's called a pseudo range. Okay? By doing this with knowing exact position of where your satellites are and being able to measure highly accurate timing, you can get great position. But it does require a couple things, as we'll talk about. Okay, so the GPS system is broken down into 3 parts, kind of arbitrarily. I wouldn't really call it that arbitrary, but it's always defined as what they call the space segment, the control segment, and the user segment. And of course, civil users, the people day in, day out, we're looking at that. That's us. We're the civil or the user segment. The space segment is dealing with the satellites themselves, and the control is primarily, that would be DoD people that are running that, and that's the monitoring that goes on. So let's look at the space segment. Space segment was developed to have 24 operational satellites at all times. So that's why it took them from 78 to 93 to get 24 total operational satellites. There's more than that up there now, and they also have spares. And some of the original satellites are still up there operating fine. So they way outlived their usefulness or what they were actually designed to do. So there's a lot more satellites up there in the global positioning system. Now, they were set up to be in 6 orbital planes, and you had 4 satellites in each orbital plane. And each orbital plane was inclined at 55 degrees to the equator. And they currently are at 20,200 kilometers average height. So it takes these guys about almost 12 hours to do 1 orbital period. So they basically come over twice a day. And because they had the 24 operational, they also built into the system 4 additional spares, so they can take satellites offline if they need to and add another one in. But like I said, there's actually more satellites up there than probably 28. And a lot of them are still completely functional from when they were originally launched. So they've really done a great job in terms of how they worked. The satellites are identified by one of 2 ways. either what's called their PRN number, which stands for pseudo random noise number. So that's the signal that it generates. And then the SVN, that's your space vehicle number. So you'll see them either both ways. A lot of people just use the space vehicle number. So you say it's satellite 5 or 6 or whatever. So when you look at your sky plots or something like that, usually what you see is the space vehicle number as opposed to your pseudo random noise number. So when we talk about global positioning, like I said, this is the US system, but of course you have other countries that have developed this same process. Russia has an equal component to what ours is, and it's pretty amazing. Their system, GLONASS, looks just exactly like this, pretty much. They use the same number of satellites, orbital planes, pretty much the same, I think, same, 55 degrees and altitude and all that. So they pretty much just copied us, but their system is equally as good as the US system. And you have receivers that can receive all these different systems. You got the Chinese system, you have the Galileo, which is the European system. If you have receivers that can receive all of these, you can actually pick up way more signals than just the global positioning system. And so instead of, we tend to call it global positioning or GPS, but really the proper term is GNSS now, because this really just refers to the US system when we say GPS. So this is kind of a schematic. This is out of your book. Kind of shows you what that would kind of look like. There's a lot of space junk up there traveling around our Earth, but these are the systems that you would see out there. And they're, like I said, they're way out there. They're in their orbital planes, and they're coming over twice a day in any one area. Okay, so the control segment is composed of 5 monitoring stations around the world, and they're very close to, well, they're not on the equator, but they tend to be kind of really different latitudes, but they're spread out. So Colorado Springs is your main, that's the main place. That's the major control. You have one in the Hawaiian Islands and the Ascension Islands, Diego Garcia and Kwajalein. So these 5 monitoring systems continually monitor the location and the signals coming from and to the satellites, and all that information is sent to Colorado Springs. So they're monitored, their orbits are tracked, and they're constantly checking out also health and those kind of issues. So the master control station is in Shriver Air Force Base, Colorado Springs. All of that monitored information that's coming from the 5 stations is analyzed, and what that's done is used to build an ephemeris and also develop clock corrections that are then sent to the tracking stations. So an ephemeris is basically a table, if you will, that tells this space vehicle, this satellite, where it is supposed to be at a certain time for a whole week. And as the monitoring goes on through the week, they constantly refine those positions, because things are going to change. They're not going to be a perfect orbit, and they're not going to be a perfect velocity. So this ephemeris is really behind what's actually happening, but it gives it a prediction of where that satellite is. And the ephemeris is developed every week, and it's uploaded into the satellites for the following week. I think they do it on every Sunday evening. So they have a time frame that they do it. So you get the ephemeris there. It's good for a week, but it's basically from data that was a week before. So again, it's just kind of a best guess. And so this is kind of a schematic, what's happening. Your GPS satellite is up there. This would be one of your ground monitoring stations. So there's two-way data. The data to the satellite from the ground monitoring station, and data from the satellite to that. But if you're just a typical receiver, the only thing you're getting from the satellite is just a one-way communication. And really all you're getting from that satellite is the ephemeris information from the satellite, and you're getting the time information it takes to get from here to here. That's all it really gives you. But then these guys can correct and upload the ephemeris, and they can also take these guys online and offline based on that. Okay, so the user segment is the civil users. Well, it could be other civil, other than civil. You have military, obviously, because that was what this essentially was set up for. But anybody that's a user of it actively is called the user segment. And there's primarily two receiver classifications or categories, what they call the standard positioning service, or it's called the SPS. And it broadcasts on what's called the L1 broadcast frequency, and there's no cost to user. The PPS, or the precise positioning service, they have what's called an L1 and an L2 frequency. And in order to get the L2, basically receivers have to have a cryptographic key, so that no civil users have access to that. And it's almost all exclusively DoD use. There's another band out there now that came online a couple of years ago called the L5, and I think they might have another one in the works actually. So there's an L1, L2, and an L5. And your receivers, when you buy receivers, the more frequencies that you can get through that receiver, the better you get. But most receivers are dual frequency, which means they pick up L1, L2. And now, of course, the newer ones also probably have L1, L2, and L5. If you have the very original first year group, or, first probably 10 years or so, most of your receivers were single frequency. So they were really limited in what they could do.
James, is there a difference in the accuracy of them?
Between the two signals?
Yeah, like I was told L1 is your most accurate.
That's that is something I'm not really sure.
L5 yet, but we're looking at.
You're breaking up. I'm sorry.
So is the L1 more like I'm on the L1 whenever I'm fixed with my GPS system?
Yeah.
So obviously I'm interpreting that being the most accurate. What's the accuracy between the L1, 2, and 5? Is there?
I don't think there's any difference. I just think when you get more frequencies coming from the same thing, that you can get the added value. Now I'm not 100% sure on that. And I'm not even sure you can read all of the L2 signal, because it used to be encoded. And that, if you notice on this slide here, the L1, the L band, it's microwave frequency, but the L1 was modulated with the precise code and what they call the coarse acquisition. And the P code originally was not available to civil users. Now that might have changed, so I'm not 100% sure on that. And even in this book, I was just reading it earlier, he says that the L2 was modulated exclusively with P2 code. So I'm not 100% sure. Okay.
Okay, no problem. Thank you.
Yeah, but I think there are ways to utilize the information, but you have to kind of do certain steps to make that happen. But yeah, I don't know. So something I could look up. We could look it up, see. But GPS is not my total specialty. I wish I had. Actually, I wish I did a little bit more with it. But like I said, some of you guys are probably using it more than I am, actually. But yeah, don't have the answer. Sorry.
No problem. Thank you.
Yep. All right. So these guys are set with very specific frequencies. They use a microwave radio frequency, so that's very high megahertz. It's 1572.42 megahertz, and the L2 is 1227.60 megahertz. So the FCC has allocated all these bands of information, for cell phones and this and that, and we have very restricted ranges for these things, and actually most of the bandwidth has been taken. So it's really hard to get anything. It took them, I think, a while to get the even L5 band. And some of you guys might recall, it probably is 5 years or 10 years ago, they were going to do a particular type of cell service. And this cell service apparently was going to be to the point it was going to step kind of on these two frequencies. And the potential was that it was going to degrade them. So there was a huge debate whether they would let that happen, and eventually I think they backed off on it, and the company I believe that was going to do it went out of business or sold it, so they decided not to do it. But if anybody's familiar with Javad equipment, anybody use that, Javad? Or, well,
I haven't heard of that. What is
yeah,
it?
well, that was the original. I think he's got another company out now. He just passed away, actually.
He reopened new. I used it about 10 years ago, but then it was sold off, and now he's got a new one, or he did before he died.
What's the new one called? You remember the name?
It was still Javad again.
Okay. All right. Well, anyway, he developed a filter that was supposed to negate the whole issue. And of course it was proprietary, so he wasn't going to sell that to anybody else, but he claimed that his receivers wouldn't have a problem if that cell service came in, you know. So I mean, I don't know if that debate has ever, or that thing has ever disappeared entirely, but that was a big debate that was raging at one point in time. So the GPS signal generates what's called pseudo-random noise, and they generate these codes, and you have a unique signal that's modulated on top of your carrier frequencies. So these guys are just kind of carrying it, and then that information is modulated on top of it. And this one has the precise code and the course acquisition code modulated on it. And this one, at one time, like I said, they only used the P code that was modulated on that, but there must be other information in there, because receivers that can get L1 and L2 have to be able to use it somehow. So I'm not 100% sure what they're doing there. But when you're saying a good example of what we're talking about by a carrier, you can think of this. I've always, when you think about light as your carrier, now this isn't light, but if you think about that and shine that through like a tube that has a damper in it, if you take that light and let it shine through the tube onto, let's say, a wall, you can see the light. But if you close the damper and then open it, close the damper and open it, what you're doing is like chopping that light down into little packets of information. And that's kind of like what your modulation is. So your microwave frequency is modulated. So this is what carries, the frequency here carries it, but then it's got this modulated information, which is called your pseudo-random noise, that the receivers pick up on. And let's see, before we step here, one thing, when you talk about this concept of pseudo-random noise, what it does is it generates a system of, you might say, on-off, on-off, on-off positions. And it looks really random, but it's truly not random. So each satellite has its own unique one. So when the receiver starts getting that pseudo-random noise information, it'll match up. It knows what codes are in there, and it'll scan it until it matches up, and it says, oh yeah, you're this satellite, or you're this satellite. And that's kind of how it matches up. So it's not truly random, but it kind of looks random if you look at it the way it's analyzed. All right, so when we look at this, there are really 3 different coordinate systems that are used. And and then of course we have the coordinate systems that we use actually 2, so there could be several more, but really it's kind of a transformation that occurs. So you basically have everything tracked in a satellite coordinate system, which is called space related. And then that's referenced down to the geocentric coordinate system, which we've talked a little bit about, but it's a little different than what we talked about the other day. We talked more about a geodetic. So you're basically transforming from one system to the other. So this is your space related. And then this one is your geocentric. This is physically related to the center of the Earth. So that's where we get that type of thing. So the satellites are really working in this system. It's transformed from your satellite coordinate system into this system. And then that ultimately is brought down to your geodetic coordinate system. So locally oriented, and it's transformed from your satellite coordinate system. And you would have another transformation theoretically if you were working in state plane. It would be translated down into or transformed in your state plane. So luckily we don't have to do any of this. All of this is done in the software end of your receiver. So when it spits out a GPS coordinate, or a state plane coordinate, I should say, basically got to realize what it's measured in is this, converted or transformed for you. So this is an example showing you your space reference coordinate system. And it's a three-dimensional rectangular type of system. This picture isn't probably the greatest in the world, but it's defined by a satellite orbit, which is essentially elliptical. Okay, so this point right here is considered the Earth location. And with your ellipse, you have the two foci, or what they call apsides. And the closest point to the Earth is what we call perigee. So as it travels around, then it goes further out, then the farthest point is apogee. So it goes always from perigee to apogee, something like that. And what you're seeing here is kind of hard to see. This is showing you a two-dimensional satellite orbit, but they're trying to visualize an ellipsoid kind of thing happening here. But they're showing you the satellite here, and if you notice, it's in an X and a Y and a Z format. So notice that the Y is coming through the Earth here. This is probably going through Greenwich. Well, it might be going through the, probably going through the equator. And then you're noticing you're going to an X coordinate projection and a Y coordinate projection, and then there's a Z also. So what you have, that's your idealized elliptical orbit, but remember, it's not going to be perfect. And then you have the two foci, and the Earth's mass center is this one over here. So what it's doing is it's tracking it based on an X and a Y and a Z in the satellite position. And that's can be transferred or transformed into this, which we call the geocentric coordinate system. So this is also a three-dimensional rectangular system. So in this case, the Earth's origin, or the origin is at your center of mass. The X of this system, the X-axis passes through the Greenwich meridian. The Z coincides with what's called the conventional terrestrial pole. So that's an interesting thing too, because the pole actually wobbles. So I believe in this system, most of the countries got together and defined a conventional terrestrial pole. In other words, one that doesn't wobble. So this one I think is aligned with that. And then your Y would be 90 degrees to this. So this is kind of like, we kind of talked about this system before, but you have what are called transformation parameters that it has to measure. So you have the inclination angle, the argument of perigee, right ascension, Greenwich angle. We're not going to get into that, but this diagram kind of shows you that. So what you see here, which is kind of nice, this is kind of your ellipsoid right here. What you're looking at, this would be your mass center of Earth. This is your X-axis coming out. So you notice this is your Greenwich meridian right there. That's your Greenwich. And your Z, this is your polar axis, the conventional terrestrial, and then you can see that the Y is over here. So if your satellite, let's say, is up here in its orbital plane, you get this angle. That's your omega angle, your gamma, or whatever angle that is, and you got these different values. So these are all parameters that it would use to transform those if you're dealing with that kind of position. So the geodetic coordinate, we've definitely talked about these. These are not typically used by surveyors, as we said, because they're extremely large, they're hard to deal with. It requires a lot of spherical trig, that kind of stuff. So that's why kind of state plane coordinates came in. But, we still use them, certainly. But what this is allows you to relate these in. And the geocentric coordinates give no information about relative elevation. So we do get, for a geocentric coordinate, we get a latitude, a longitude, and an ellipsoid height. Okay, so the ellipsoid height is very important, and that's the only elevation parameter that GPS actually gives us. So that's the distance above or below the ellipsoid at a certain value. Let's get this diagram. So this is kind of a good diagram, and this is showing you This is showing your X, Y, geocentric coordinates. Then of course this would be, if this is Greenwich, if this is our satellite right here at that position, what we're looking at is you've got this plane right here, which would be a meridian plane. This plane right here, that's a meridian plane. So the angle from Greenwich over, that's your latitude, or longitude, excuse me. And at that point on the ellipsoid, if we run that down into the plane, what we're getting here is this angle here. That's your latitude. And then the distance, this is the RN, that's actually the radius above or from the center out to that point on the ellipsoid. And this HP is representing, that's your ellipsoid height. So that would be the difference up. And you can see here's the X coordinate, the Y coordinate, and the Z coordinate. So those are the geocentric, and then these are the geodetic essentially, which could then further be translated into, like we said, state plane or any other local UTM, any of the other local map projection types of systems that you have. So kind of the bottom line is just remember that you have the 3 different systems primarily, and it's primarily working in that space segment type of system. So some things about the fundamentals, and we're not going to get like super in depth on this, but basically it's essentially just dealing with a time. And what we're getting when you're setting up your receiver, you're just reading information from the satellite. So the satellite sends out its pseudo-random noise signal. Once it syncs up, it knows how long it takes to get from the satellite's position to the receiver. So you just get, it says you how much time it took, and it also knows its relative position based on this and the current ephemeris at that point in time. And so at 20,200 kilometers, that signal takes approximately 7/10 of a second, or 7/100 of a second to reach that receiver. So essentially, if you have a time t, that's your elapsed time from the time it left the receiver or the satellite to the time you picked it up. And we know that the speed of light in a vacuum is c. So we're basically taking the speed of light times your time, and that gives you a range. So that's your distance essentially. And by knowing your distance and also the position of the satellite, you can then get a fix on the Earth. But you can't just do it with one. So you have to do it with multiple satellites that are giving you multiple ranges. And these ranges are all, which is a distance essentially, but they're also referred to as a pseudo range, okay, not exact. Well, the other thing about the speed of light, all electromagnetic radiation, which a microwave is in the electromagnetic radiation spectrum, they all travel at the speed of light in a vacuum. But what's happening is you're not in a vacuum totally. So the satellites are up in space, deep space, so that's a vacuum. But then we're going to hit through the atmosphere, particularly the ionosphere and the troposphere. And those two things are going to really screw with the time is what's going to happen. So this speed essentially slows down once you get into it, because I always like to equate it to the fact that you're going from, like, say, air into a fluid. So the fluid is more dense. What's happening is that slows that down. So that stuff has to be accounted for. And some of it can be modeled really effectively, and some of it's a little bit harder to model. Here, we'll talk about that in a minute. So there were 2 kind of fundamental methods that are employed by GPS receivers to determine distance. One is called code ranging, and the other one is carrier phase shift measurement. Okay. And again, a lot of this has changed over time, so some of this is a little bit dated. But code ranging was always considered mapping grade receivers. In other words, lower class receivers, or ones that just didn't have the ability to do as well. They probably didn't have as good a clocks in them. And the carrier phase measurements were considered survey grade receivers. So most of what we would be using would be considered survey grade receivers if you're doing any GPS surveying. But if you're out there just like locating manholes kind of thing, handheld GPS, you're not doing much, that would probably be this kind of thing, code ranging. So code ranging, with your signal travel times known, your distances can be calculated. With the range to one satellite, the receiver would lie somewhere on a sphere. So if you think about wherever that satellite is and it's just sending a radius out, that's the time, the distance over that time, but it would generate three-dimensionally, you'd get a sphere. So obviously that's going to be not enough to tell you where you are. So if you have the range to two satellites, what's happening is it's got to lie where those two spheres intersect. So where two spheres intersect actually generate a circle. So you would have a big, again, area of location where you would be. So a third range kind of locks it down. It gives you two possible locations that it would exist. But obviously one is going to be erroneous because usually it's going to be above the Earth and the other one's going to be down it. So basically you can do it with three receivers, but usually you're going to want to use a fourth or a fifth or a sixth, because then we can start to take out some of these other errors that we talk about. So this example is in your book. Now this is showing this two-dimensionally, so you got to recognize that what we say is, okay, let's say this represents your Ann Arbor, Michigan, but you're 50 miles away. So you set up a receiver or whatever, and you're 50 miles away from Ann Arbor, but that's all you know. So you notice it could lie anywhere along this thing. Okay, we add another location. All right, Traverse City, that's say 150 miles away from where we are. So where these guys intersect two-dimensionally, you have two locations. But remember, if these are spheres, there's actually a circle around here where these two intersect. And if we add a third one, okay, from Kalamazoo at 60 miles, this would be a lock, okay? But again, with GPS, you would still basically have, because there's a circle here, you would still have two unknown, or really a whole bunch of unknown locations. So we actually add fourth at least as a minimum. So usually, I mean, you could do it with three, but four or more is going to typically be better. There's a picture here, and this is also in your book. This shows it a little bit better. So you notice you got a receiver set up down here somewhere. This satellite's giving you information, that range, so it generates this sphere, and this satellite's giving you this, so it generates this kind of sphere right here. You notice where the two spheres, that one and that one, intersects. You have this area here, and once we intersect that with a third one, you got two possible positions that could exist on that. Now, one is obviously going to be way higher, so it could be weeded out because this one would be way above the Earth, and this one would be down. The one you're talking about. But realistically, that's probably not good enough for surveying, so we would want to add more. So the more intersections that we get, the better we get. Okay, code ranging, what it's going to use is a little bit more math, and we're not going to go into it, but essentially you can notice what you're looking at. This is the Pythagorean theorem, essentially, in what they call an XYZ triple. And so what you're doing is these are positions from, I think A is the position of the receiver and 1 is the satellite. Okay, so that would be space vehicle. So there's your difference in X, difference in Y, difference in Z. And this is the second satellite and the third satellite. So what you're generating is a system of equations where you have unknowns in there, but by having multiple equations and the same multiple unknowns, you can generate it simultaneously. So this would be called your rho 1 to P is geometric range, where that's your space number and that's your position. And then you have the geocentric coordinate values from the satellite. So these are what the satellite's providing. And what you don't know is this right here, essentially. So by generating this simultaneous equation, you can solve it. So code ranging. So when you obtain any kind of good code ranging value, you have systematic errors associated with your numbers. Well, that's true with any measurement, as we know. Two classes of errors associated with any measurement. We have the systematic and the random error. So systematic, if you recall from your measurement stuff, are types of errors that can be deleted because they can be measured and then you can apply a calculation to them. The biggest deal when you say that, though, is you have to observe what's causing that error. So, a good example is a temperature correction with a steel tape. that's a good example of a systematic error. We recognize that tapes will increase or decrease distance with increasing or decreasing temperatures. So by measuring the change in temperature and using the coefficient of linear expansion for whatever material you're using, you can predict the amount of error that's associated with that measurement, and then you can also, you know which way it's propagating, positive or negative. Well, the same thing's happening here with these types of systematic errors. Because of that, we can do that. So we have two major things: clock bias and wave refraction. Now, wave refraction is probably a little bit harder to observe, but clock bias is actually easy to resolve. So when we include a fourth satellite in the range, we can basically get rid of that clock bias, or actually determine it. So that allows us to measure that. So the reason we do that is the clocks that are on your receivers are just basically quartz crystal type things, but the ones in the satellites are very, very precise atomic clocks. So they use rubidium or cesium, I believe. So they're measuring at a much higher level of time than what your receiver is. And obviously you don't, because both of those things are radioactive, you don't really want people walking around with radioactive receivers. So by allowing them to adding this fourth, you can determine clock bias. Since it's a systematic error, if we can determine it, we can determine the amount of error that is associated with it and whether it's a plus error or minus error. And so they use that technique. So code ranging, again, it's another system of equations that's a kind of a simultaneous thing used to solve your receiver position. And if we look at the variables here, R 1 over A, 1 is your satellite. That's referring to your satellite. So notice they're showing you're using 4 satellites here. A is the position of the receiver. And this is then referred to as your pseudo range. You can see the geometric range. This is rho, which we just calculated before, time t. And then there's your speed of light. And then these are biases. You have a satellite bias and a receiver bias, and those are timing things. So carrier phase shift measurements give us better accuracy in measuring our ranges. And what we're doing is really measuring that phase shift that we were talking about before. This is kind of really similar to the way EDMs work. So EDMs don't really measure distance. They send out a beam that's chopped up into little increments of distance, and it comes back and it measures how many partial increment, what partial increment came back. And it will do that different times with different frequencies to do what's called resolving your integer ambiguity. So once you do that, once you do the integer ambiguity resolution, then you can determine what distance is. This does require longer observation times. At least it did at one time. Part of that reason was we didn't have as many satellites out there. I think because we have the inclusion of satellites and other things like core stations and that, timing has gone down a lot from what it was in the original days. So let's take a look at some of the errors associated with GPS observation. Electromagnetic radiation or waves are going to be affected by a lot of different sources of errors. You have the satellite receiver clock bias. You have the ionospheric and tropospheric refractions. Okay, and again, these things tend to slow down what's going on. And it's really hard. The ionosphere can change pretty drastically depending on what the sun's doing, because it's kind of like charged particles up there. So this one's harder to model than this. Your satellite ephemeris errors, remember, the satellites only know where they think they are based on what the DoD has sent to them at a particular time. That information is not updated till almost a week later. So you can do post-processing and get better results, but if you want to do it right away, then you're going to have to do other techniques. You also have a process called multipath, where the line of sight is not coming directly from the satellite into the receiver, it's bouncing around. So if it's bouncing around, it's taking a longer time. If it takes a longer time, that gives you a longer distance. So that will give you an error. Antenna miscentering, this used to be a big deal. These two things right here are probably moot any longer. In the original days of GPS, you had a satellite or a antenna that you set up on a tripod. You had to measure it exact, and you had phase centering issues and all kinds of stuff. Most people just stick them on a 2-meter pole. They're fixed. Everything's set. You don't have to worry about that. So these two kind of things have really changed quite a bit from what they used to be. But we still have to deal with some of these other issues. Okay, so a clock bias is a systematic error. Your satellite clock bias is modeled by broadcast message coefficient. So again, that's one of those things they're going to monitor constantly, and then they'll check it, and then they can update information to it and from it. So for relative positioning, that can be removed through post-processing, but a lot of people don't like to post-process. They want to know an instantaneous answer. So there's other ways that you can get rid of those things. Receiver clock bias is treated as an unknown, and it is also eliminated during post-processing. So remember, the satellite clock is a lot better. So the bias is probably, the error associated with it is probably pretty small as compared to the receiver clock bias. That's going to be a little bit bigger because, again, it's using a much cheaper means of timing. So ionospheric and tropospheric refraction, these can be big things. And basically, you're going from the atmosphere, or from the satellite, which is in a vacuum, to the Earth's atmosphere. And once you hit that atmosphere, the light, or not the light wave, but the microwave bends a little. Okay, that's called refraction. And as you do that, of course, the refractive index, it bends it, but it also tends to slow it down. So this is going to produce range errors similar to timing errors, because what that's doing is it's basically increasing the distance. So if it's increasing the distance, theoretically it's increasing the amount of time, which ultimately goes into the timing of the total distance from the satellite to the receiver. So these can be eliminated using mathematical techniques, and two signals that two receivers pass through nearly the same atmosphere. So they'll do that a lot to get them out. Now, again, a lot of people are just using single receivers, but they're also getting their corrections maybe from a base station or a core station or something else. So ionospheric and tropospheric refraction, the troposphere is from 10,000 to 20,000 kilometers in altitude, and it includes the troposphere, the stratosphere, and the tropopause, which is that's a layer between the two, essentially. So the ionosphere is a lot higher up, and it's composed of ions and free electrons. So what's happening is those things can scramble or interfere with the signal. It definitely affects your wave propagation, and it'll typically be dependent on what the sun's doing. So if we have a lot of sunspot activity, which kind of has a 14-year cycle or something, sometimes you get more activity than less activity. So that can really affect things. And this is the kind of stuff, this radiation that the sun sends out is when you get like auroras and those kind of things. So when you have that kind of stuff going on, you got a lot of ionospheric stuff. These are a little bit harder to model because we can't really say, what the sun is doing at any one time or how that's really interacting and affecting these ions and free electrons. So that one's a little bit more involved. So this is out of your book, and this is kind of showing you a really good example. So what we're saying is this area right here, this is your total vacuum. So at this point, this is actually traveling at the speed of light, but at this point right here, it refracts. So this is showing you that bending, it refracts, so it alters that propagation. So this is your ionosphere, where all those charged particles are, and then it hits another area here where we're getting into the troposphere. Remember, it's broken down into several different types of things too. And you have things like moisture, humidity, whatnot down here. That kind of affects things, but not quite so much as this. But when it hits there, it bends again. So really what you can see is that's kind of a nice way of showing that distance has been increased. And again, distance increase changes into a time increase, okay? So low altitude signals are another thing that can be a problem. And And we usually like to omit those from an observation, because what happens is the lower the satellite is on there, the worse you're going to get. Data is better overhead more, but the opposite of that is you don't want all your satellites right overhead. Okay, you want them spread pretty nicely, but you don't want them down here, because that can actually increase. It hits that atmosphere kind of at a low angle, and it actually takes it longer. So what a lot of people do, and most of your receivers or your controllers anyway, have what's called a mask that you can place in it. It's a mask angle. So if this is set up here truly horizon, you put a mask angle, and correct me if I'm wrong, I think most people use about 15 degrees, something like that. Does anybody know what they're using?
I think it normally defaults to 10,
10, okay.
and then
So
yeah, sometimes it increase to.
you can increase it to like any value you want, essentially, for whatever use, but you just don't want low angles here. So that's called a mask. Particularly like if you were in an area maybe where you were had a little bit more obstruction going on, you could even set that mask angle up a little bit higher. So a satellite ephemeris errors, let's talk about those. The ephemeris predicts your position of your satellites. Remember, that was calculated basically a week ago based on all the tracking from all the observing stations that they have there. So your actual orbit is really always going to be somewhat different. So when the ephemeris tells you that you're at this position, X, Y, Z, it's really not. Obviously, that's going to play into the error of your position down on the Earth. So the problem can certainly be reduced by using your updated or actual orbital information, but you're going to have to wait until that's processed. So that's usually done through a post-process data. Okay. And that was the way a lot of people used to work. Again, before we had all the satellites, before we had GLONASS, before we had cores, any of that stuff, a lot of everything was done post-processing. So you don't even hear that term post-process used much anymore, because it's just not as common. But the post-process survey ephemerides that are available, you get what's called the rapid ephemeris and the precise ephemeris. And both of these are downloaded as part of the signal when you're getting that. So besides the pseudo-random noise, or within it is embedded areas that contain the ephemeris data as well. So another problem with receivers is a process called multipath. And so this is caused by reflection of your signal from usually a smooth surface such as glass or water can cause it. So what it does is your signals arrive at different times. So notice if this would be the normal path, if the path is coming in and it hits this building, it obviously takes it longer. So this is what we call a multipath signal. So if you've got this kind of thing going on, it can be a problem. There's a couple of ways to get rid of it. One is they used to use what's called a ground plane. Most people don't use them, but it looked like a big plate that they would put on their antenna, and it would keep them from, if something was coming in low, bouncing up and hitting that way, it wouldn't come into the satellite or the antenna. And the other thing, of course, is you just got to watch where you're setting up, okay? If you have things like this going on, like a glass building, a wall with glass in it, or a lake or something, you don't really want to set up there, because you have the potential to get mount multipath. So things like vertical reflective surfaces, those are going to be very definite sources, and water can also do this. So antenna miscentering and antenna height. Any type of antenna error, either vertical height or miscentering horizontally, is going to translate directly into equal sized error in your position. So this was really, really critical, this antenna height error, because it absolutely just screwed up your ellipsoid height. And so that was really, really important. And of course, like in the early days, like I said, I set these up years ago, so a lot of this doesn't even matter anymore, because the antennas are usually matched already to the system. You guys don't even have to worry about this. But in the old days, you had all these different antennas. You had to measure to the phase center. You had to know, what the orientation was, frequency. You had to key all this into your controller. And any if that was off just a little bit could translate directly into errors associated with your ground position, and particularly the ellipsoid height. So if you didn't measure your heights correctly, that your antenna was above your position on the ground, it really just made a huge mess on your vertical position. You still got pretty okay horizontal position possibly, but vertical position was just going to be a mess. Okay, so we talk about errors associated with GPS observation. Again, probably should switch this over to GNSS errors, because this is really true for any type of system that you're using. But remember, GIS, when we talk, or GPS, when we talk about that, we're really talking about the US system. So we have a couple of different kinds that we talk about, and these, what we call the geometry of your visible satellite constellation at time of observation. So the two things that you look at are the number and the position of visible satellites before you do kind of any really major control survey. And again, this is not as a major a deal as it used to be, because nowadays, especially if you have a receiver that is picking up GPS, constellation, GLONASS, maybe Baidu, Galileo, you're getting a lot more satellites. So you're getting both their positions and then a lot more satellites you can deal with. But you have to deal with what's called this dilution of precision. It's called DOP, and there's several different ones. PDOP, which is position dilution of precision, HDOP, horizontal, VDOP, vertical, and G is geometric. And most people that I know really just kind of look at this one. That's the one that most people look at anymore. Some people don't even really care about those too much. But what this will calculate for you is a number, and the lower that number is, the better your position is going to be. So we're looking at category. Basically, this is just a position. It's kind of a delta X, delta Y, delta Z kind of thing. And notice that's just, again, a triple. Acceptable value by this, when I wrote this, is 6. You really probably want to be lower than that by today's standards. HDOT, we were looking at 3. VDOT 5, and I don't even think they have geometric position. So in your controllers are typically going to be shooting out what your numbers are here, and they can tell you. Some of them, I believe you can have them quit reading if it reads above an acceptable value that you have placed in your controller. So the controllers are, and the software, I guess, is so smart anymore. We really don't have to deal with a lot of this, but in the early days of GPS particularly, this stuff was extremely important to look at, and you had to really focus in on this kind of stuff. So another type of error that was associated with GPS was called selective availability. And that was actually intentionally developed by the government and placed into the GPS signals. So they would degrade the accuracy or reduce it. So the intent was to exclude any high accuracy measurement for non-military users. So it really degraded it by, like, say, 100 meters in position. So they employed 2 methods to degrade it. They used what was called the delta process and the epsilon process. We don't need to worry about that too much. But again, just what it did was it delayed, or it deleted, or not deleted, but it encrypted errors into the messages. So this was a problem if you're trying to do real-time stuff, but it wasn't a big deal as long as you did post-processing, because you get rid of it. So the combined effect of the 2 errors when you had selective availability on was 100 meter horizontal and 156 vertical. So that's quite a bit. And that error could be removed by doing differential positioning techniques. So those were ways of doing that. But again, it was typically done as a post-process kind of thing. So it wouldn't have been work. You couldn't have done it on the fly real easily. But it was permanently turned off by presidential directive May 1st, 2000. So we haven't had to deal with it for almost 20 years. From what I understand, I mean, that could probably come back at any time if they wanted to. But I've also, from what I understand, some of the satellites don't even have the capability to do this anymore. So some of the newer satellites, they've actually taken this out completely of it. So, but it does make sense that if you want to have something like this in place, the DoD, I mean, it does make sense that the military could do that if they needed to. All right, so that's the first thing. I wanted to show you a couple of things here. Also, let's go to this next slide. And we're not going to spend too much more time here. Let me grab this real quick. So let's see. You have this group of slides. I'm not gonna, a lot of this field stuff. Let me pull this up real quick. So there's just a couple of highlights I want to show you in here. So some of the things that you can see in here, it talks about GPS field procedures. Again, some of this is quite dated. So you can use this just to read through. This is stuff that's not in your textbook. Most of what was in the textbook that we're using was just the stuff I went over. And planning surveys, we don't need to worry about that, or performing static. What I do want to show you is some of these errors. So let's bang up to that a minute, and then we can be done here. Let's see. Let's see. I'll be there in a minute where I want to get to. So much of this has changed anymore because of the way we're doing the RTK stuff. This all predated a lot of that, so we don't even need to talk about it too much. You might want to read through some of this though, just to kind of see, because this stuff was what you were doing 15 years ago, maybe. Let's see. Well, planning is still pretty important. One of the things that you need to do if you're going to do, and what we're talking about is probably more control, but planning any kind of project, there's a critical components associated with that. For smaller GPS surveys, you don't need to do that much, but if you're doing like a big highway corridor or something, large project, high accuracy survey, control surveys, planning is still important. So some of the things they have to consider is getting relevant horizontal control information that you can tie into. So somebody has to go out and do reconnaissance to confirm the condition and whether they're finding this stuff. And then if you're going to set new control monuments, you certainly have to look that you're meeting all the overall objective. It's got to be accessible and certainly free from overhead obstructions. And there's a typical 15-degree mask, possibly. Okay, so let's look at this, because this is what your lab's going to be dealing with, is talking about these windows of observation. So what you can do, which is kind of neat, and we're going to be looking at the Trimble software, you can select your suitable observation window. What this will do is determine for you the visible satellites, and it'll give you things like your DOPS and those kind of things. But what you tie in for your mission planning software is the date, the time frame that you want to do it, your approximate latitude, longitude, the elevation mask you're going to use, and then you use the current satellite almanac. So this is showing you software that will kind of show this, and what this is demonstrating to you, it's showing you at a particular latitude and longitude, and notice I think this says it's at San Diego. There's your latitude and longitude and your current time range. And so what this is showing you is the differences wherever you're planning to set this observation at. This will give you the best times and the worst times. So the higher the numbers go, notice we've got geometric, position, vertical, horizontal. So PDOP is what most people look at. The top of the green is essentially what you're looking at, and as that gets higher, notice as it spikes higher, this would be the worst time to do your observations according to this chart. And if we're looking at the best time, it looks like it's probably down over here. Notice that's a pretty small window. But again, this was probably done, I'm not sure, the date here is 2007. So, I mean, things have changed quite a bit, but this is just planning software that we're going to be looking at. So you're going to kind of get a sense of how that works.
I wish I would have had that 3 weeks ago.
Oh, yeah?
Yeah, I went out on rented a VRS just for some rough staking, and went out on a Saturday morning and worked for an hour. Great. And then all of a sudden, I couldn't get anything.
So you lost your window?
But I didn't realize why. Yeah. So then I said, okay, I'm going to come out Sunday. So I came out Sunday for the same time frame, and daggone it, it did exactly the same thing.
Wow.
So then the next day I came out earlier, and worked it out. Luckily, I only had an hour and a half worth of work to do, but
Right.
I didn't realize that this was available.
Well, actually, you can go to Trimble, and that's what we're going to do. You're just going to go to Trimble and use it. It's free. So, you just type in basically your latitude, longitude, and that's the lab we're going to look at. But that's good. If you learn something like that, that's great, right? That'll help you in the future.
Yes.
Yeah, cool. All right, so this is showing you, this is, notice it's SV, so those are space numbers and PDOP associated with each unique satellite. So there's your space numbers, and what satellites are available. Notice, of course, remember, lower is better, right? So we'd be looking for the lower numbers here. This would be a bad time to do anything, okay? And primarily because what's happening, notice as the number of satellites go up, the PDOP drops, which should kind of make sense. But that also has to do with where they are in the sky. So if you have 10 satellites overhead, that may not be as good as having 5 satellites that are equally spread, okay? So the geometry of the position of those satellites during your time of observation also makes a difference. And this is called a sky plot, if anybody's never seen one of these before. And a lot of times your controllers will show you this. You can pull these up on a controller. So it'll show you, you're basically at the center, and this is showing you your horizon, and that dotted line, that's your mask. So basically from horizon to mask, it says even though satellite 6 is available during my time of occupation, it's masked out. So notice also as 30 is, and 4. And 13 is out of the mask, but it comes into it, or I'm not sure which way it's going, this way or this way. But so notice though, these are actually pretty good configurations. You got 29 over here, space vehicle 25, 22, 20. And so we can see that what's going on there. And again, with nowadays, if you're reading, GLONASS and GPS and all that, you're going to have a lot more satellites that you're tracking.
Yeah, from my experience, if you have satellites that are real low in the sky and they might be getting in the trees, or if it's just real low in the sky and there's interference off in the distance, sometimes just by increasing your mask or turning that satellite off, you can get a good solution.
Yeah, it gives you, you're saying basically it drives your PDOP low, right?
Right. Yeah.
Yeah. And that,
yeah, one bad satellite can ruin the solution sometimes.
Absolutely. So you definitely can, like you said, you can kick them out, right?
Yeah, you can go in, at least with the Trimble collectors, you can go in and turn individual satellites off, or you can just increase the elevation mask.
Right. Increasing the mask is easy, and I think both things I think you said were pretty easy, and I think that's pretty standard on most of them nowadays.
As far as I know.
The other thing is occasionally, the DoD puts out that certain, like satellite 25 is giving you bad observations. They'll either kick it off, but they may not turn it off for you to use. But you may have to figure out that, like you said, you got a bad satellite or a bad reading. You might get that with GLONASS sometimes, where we don't have that information. So yeah, this is a cool little thing though. This sky plots. In my experience, I've done a lot of little stuff that's kind of where I'm using a handheld one, but the sky plot on there, routinely you're probably getting 12 satellites or more, where we're working a lot of times. And you can see you're getting quite a few, but that mask is kicking a lot of them out. Okay, so I think, let me see, it's probably about really, this is all planning. Field reconnaissance. I think probably a lot of that has to do. You could read through this. There's some things about errors, but I think we kind of already talked about that. Let's see if there's anything in here. Well, let's look at this real quick. So there are some natural errors of refraction, relativity, multipath. We talked about those. But there are some interesting things under the sources of error, instrumental errors. You got the clock bias error, setup errors. Again, a lot of this stuff is not as important anymore, but we've already talked about your clock bias. But both the satellite and the receivers are subject to errors, but the satellite is going to be a lot more precise, so your receivers have more of the bias issue. But by doing those differencing techniques, we get rid of those. Instrumental error, selective availability, that really is not something anymore. Sometimes receivers, if they're cheaper, you get that random error noise, just in the signal processing. Natural errors, refraction, we already talked about that. That's your transmission through the atmosphere. That can be resolved pretty easily. This is a pretty interesting one. People don't even think about this, but natural error due to relativity, and that had to deal with what Einstein was dealing with when he talked to, as general and specific theories of relativity. But the speed of the satellites cause the atomic clocks to slow. That's predicted by relativity. So that's an error that's associated with the speed, velocity. So master controls can compute and correct those clocks based on that. So without tracking, that would be something that's very important. Yeah, I think we talked about most of this, so I think we're pretty good. All right, so let me bring this back. All right, so really, I think that was pretty much everything I wanted to go over today. Does anybody have any questions, comments, anything they want to talk about?
One question that I have is that a few years ago, rented a VRS and went out and got coordinates on a point outside my office.
Okay.
The next day went out and got coordinates on that same point, and were just 0.05 difference. Would that be because, or if I would use post calculations on that, would that have corrected that out?
It probably would have. Yeah, that would be my guess. Because if you're getting, basically you were just reading what's called autonomous position, but VRS is giving you corrections, right?
Yes.
So autonomous position means you're just getting it without any kind of correction. VRS is getting it, but you're probably just getting changes in what's happening, day to day. But if you post-processed, yeah, you could probably refine that down. Yeah.
Yeah, I've seen variations with the VRS up to 2/10.
Up to 2/10, really, Ben?
Yeah, in horizontal position.
Yeah, that's pretty
crazy. Ben, was that day by day? I mean,
yes.
Yeah.
Because what happens with the VRS is it creates a network solution. It's not taking a single base station. So it's day to day, and it's based on position. So it can vary slightly.
So essentially, it's floating, right?
Well, it's not floating.
Well, I mean, the system's somewhat floating, is what I mean. It's not like a stable, like a core station. That's what I'm getting at.
Well, yeah, it's collecting information from certain number of core stations that are within the vicinity of you, and it uses your position, and then it takes all that into account when it calculates the position.
But if 0.1 was 0.2 off, 0.2 would be 0.2 off, 0.3 would be 0.2 off.
Right.
It's all relative.
The error will be relative. Yeah.
Yeah, that's what I noticed too. Yeah.
Yeah, it definitely should be relative, right?
That's why I generally I've preferred just to, if I'm doing anything that needs besides just topo, we'll set control and shoot it all with the gun, because then we get consistent results.
And an easy way to post process, you just send that off to the NGS and let them cook it for you. And that's a lot of people use their positioning service anymore. A lot of people don't even post process; they just send it out. It's a really good way of doing it. Okay, good. Anybody else questions?
Nope.
Okay. Well, I'm going to go ahead. I'll stop this recording, and then we will. I'll post that up there. For Thursday, we're going to be looking at that little Trimble software stuff, going through that, and I'll be answering questions about the test that's coming up. I will be catching up on stuff hopefully soon. I've been working a lot to get this done, but it's just taken a while. So
Do we
hopefully-
have any quiz or anything this next lab?
Yes, we'll probably have a quiz over chapter 3. Yep. coming up,
Okay.
right. And then the following week RBR test. So think about some questions that you want to ask about that too. We'll talk about that. Okay. And if nobody else has any questions, then we'll stop the share and see you guys on Thursday.
All right. See you later.
All right. Great.
Thanks.
See ya.
Bye now.
See you.
Bye.